So we said this builds, and it begins with this, solving equations of the form trig function equal a number. First thing we want to be able to do is that. And to solve these, what we do is let theta equal whatever angle is in the trig function. And then we can solve for that on the unit circle, right? Using inverse trigonometry. Solve for all possible theta. Then part C, if the angle isn't just theta, maybe theta is equal to 2x is the angle, we then have an algebraic equation to find x. So from theta find x, and then it may be restricted to x being between 0 and 2 pi, right? We might only want to know the direction. We may not want 17 pi over 3 to be a solution. We just want to know what direction it is. So we might apply some restriction, if any. Apply the restriction that 0 is less than or equal to x less than 2 pi if required. That look familiar, I hope, what we did last time. So it has this kind of example. Let's take it over here where I've got more room. And since we're not at a beginning example anymore, I'll do a hard one here. Suppose I had a tangent of 2x equals -1. How would I find all solutions x between 0 and 2 pi at one rotation? Maybe I better stack it up just a bit. You follow the recipe here, right? Let theta equal 2x. You get tangent theta equals -1. Once you have that, you can solve it on the unit circle, B, right? I'll put the circle like that. And for tangent to be -1, how do I solve for that on the unit circle? Remember, tangent and cotangent are the hard cases. Let's find that. Tangent theta is supposed to be the ratio y to x on the unit circle, right? So I have to write this as a ratio. Let's write it as -1/1. And that's still not good enough because -1 for y and 1 for x is not a point on the unit circle. How do I get a point on the unit circle with that ratio? First write a ratio, then get a point on the unit circle in that ratio. The way you do that is you divide top and bottom here by the root sum square of those two numbers. -1 squared plus 1 squared is square root of 2, right? So I'll divide top and bottom by square root 2 and write this as -1 over square root 2 over 1 over square root 2. And now it's a point on the unit circle. What happens is this for y and this for x, or x for y if you're doing cotangent, is a point on some circle, right? A certain distance out, and the distance is this. This point -1, 1 minus 1 is square root of 2 units from the origin. So this is a point on the circle of radius square root 2. If you divide the coordinates by square root 2, it brings them that far in and puts them on the circle of radius 1. That's what that's doing. And so now this is a point y, x on the unit circle instead of a point x, y, x on the circle of radius square root 2. But there's one more point on the unit circle that has that same ratio. What is it? I better put this up. What's the other point? Always the opposite direction, it turns out. This is hard to remember, isn't it? You can take minus this over minus, it'll have the same ratio, right? So if I take plus 1 over square root 2 over minus 1 over square root 2, that's the same ratio. And so that'll be a point on the unit circle too. And we need both of them. It's not like when we were saying which one is the arc tangent and only one of them was in quadrant 1 or 4. Here we want all solutions to this equation. So we can sketch both these points. X equals 1 over square root 2 is about 0.7. Y equals minus 1 over square root 2 is about minus 1.7, 1.7. And so if I leave a little room for it here, it's around here. The other point is with y positive and x negative. Got to be this point, and they're always directly opposite for tangent and cotangent. And so there's exactly two terminal rays where the y to x coordinates have that ratio. Well, of course, it's just this line of this slope, so that y over x is that slope, -1. It actually splits the axes there. So in part B, you find all theta. Here's a couple of them. How can I find them? Well, you can drop the perpendicular in the unit circle and say, well, this is minus 1 over square root 2 here, so the length of the side is plus 1 over square root 2. That looks kind of familiar. What does that remind you of, 1 over square root 2? Yeah, if you rationalize it by multiplying top and bottom by square root 2, this is also square root 2 over 2. Aha! That's a triangle I memorized, right? 1 square root 2 over 2. This would also be square root 2 over 2, which I can guess from this goes up to 1 over square root 2 here also. But what I need here is the angle, right? I'm trying to find the angle theta that gets there. And so I look at the reference angle first, and I say, this is a 45, 45, 90 triangle. I know from its sides. Pi over 4, we're going to do these in radians. So what is theta? The angle in standard positioning that gets there. That's what I'm looking for, theta. The angle theta is in a straight angle back up pi over 4. So pi less pi over 4. I have to put it over a common denominator to subtract quotients, right? So I'll write that as 4 pi over 4 minus pi over 4. It's 4 pi minus pi is 3 pi all over 4, right? Pi minus 1/4 pi is 3/4 pi. That's one angle, and then what's the other one? That. Yeah, 7 pi over 4, right? Because if I drop the perpendicular here, this will also be pi over 4. There's always symmetry. They're opposite directions. So this is also pi over 4, I suppose. And so 2 pi back up pi over 4, this angle, which is 8 pi over 4, multiplying top and bottom by 4 here to get a common denominator, less pi over 4. 8 pi minus pi is 7 pi. Oh. So there's the two angles that I have. Part B, to solve for all possible theta. That would give tangent theta equal -1. Is theta equals this angle, 3 pi over 4. Leave a little space, or the other one, 7 pi over 4. Well, that's only theta within one rotation, though, right? We saw there's only two terminal rays, but there's actually an infinite number of angles that have those terminal rays, right? Because all coterminal angles means terminal rays coincide. Also have these terminal rays. So that means you can add a whole number of rotations. 3 pi over 4 plus k rotations, k times 2 pi, right? Except we said we don't usually write k times 2 pi, we write 2k pi. It's just convention, yeah. And that means k rotations, where k is any integer, right? 0, 1, -1, 2, -2, any of those numbers. Infinite number of, so there's an infinite number of angles that have those terminal rays. Those are all the angles coterminal with these two. The other one is 7 pi over 4 plus 2k pi. And then did you remember how we can write that equivalently a little shorter? How can we write that shorter?
Pi over 4 plus k pi.
Yeah, when they're directly opposite, you can take one of them, 3 pi over 4 plus pi plus pi plus pi, and get all of both of them. So equivalently, for brevity, I'll just write 3 pi over 4 plus k half rotations, k pi. That's a lot easier than writing this, right? So let's write it that way and say that's all possible theta in part B. And now we'll say from what we get for all possible theta, we try and figure all possible x. The original variable. Well, I just put 2x is equal to theta is equal to 3 pi over 4 plus k pi. And solve for x by dividing by 2, right? Equivalently, x is, you have to divide the whole side by 2. See how good this makes you in algebra, makes you do all those quotients over common denominators, divide the whole side by 2. So this is 3 pi over 8 plus k pi over 2. There's all angles x. But this one has a restriction, right? We want x only between 0 and 2 pi because we only worried about the direction, not about all rotations. So now all x between 0 and 2 pi within one rotation. What are those? I just try plugging in various values of k and see what works. So I try x equals, if I put k equals 0, does that work? I get 3 pi over 8 plus nothing. That's between 0 and 2 pi, right? It's positive. 2 pi would be 16 pi over 8. So that's certainly less than 16 pi over 8. That counts. Now that's k equals 0 in that equation. Now I try k equals 1. Pi over 2 plus 3 pi over 8. Right in the other order, I guess. 3 pi over 8 plus pi over 2. And then I have to put them over a common denominator to add them, right? So that's k equals 1. 3 pi over 8 plus 1 pi over 2. Well, let's put them over 8. Let's call it 3 pi over 8 plus 4 pi over 8, multiplying top and bottom by 4, gives me 11 pi over 8. Well, that's also less than 16 pi over 8, 2 pi. So that one counts. That's k equals 1. Let's see. That's not 11, that's 7. Gotta be able to add in this one too. 7 pi over 8. I'm jumping ahead to the next one. The next one, if I put in k equals 2, you don't have to list these k's down here. I'm just doing it for clarity, hopefully. If I put k equals 2, it's now 3 pi over 8 plus 2 pi over 2 is pi. Well, this is 8 pi over 8. 3 pi over 8 is 11 pi over 8. That's between 0 and 2 pi. So k equals 2 also works. I get 11 pi over 8. And then if I put k equals 3, now I've got 3 pi over 8 plus 3 pi over 2. K equals 3. Well, again, this is 12 pi over 2 plus over 8 plus 3 pi over 8. If you put over a common denominator, makes it 15 pi over 8. And you start to notice that there's a lot of symmetry, right? 3, 7, 11, 15 on some of these. That's k equals 3. And then k equals 4. Well, k equals 4, this becomes 2 pi plus a positive angle. I don't even need to figure it. It's 2 pi plus something is too big, right? I don't want to restrict theta or x between 0 and 2 pi. If I put k equals -1, let's see if that works. That's negative pi over 2 and 3 pi over 8. Well, let's see, this would be minus 4 pi over 8 plus 3 pi over 8 would be negative pi over 8 is negative. So if you try k equals -1, it's negative. That's too small. Try k equals 4, it's too big. Only these 4 values of k work. There's all the solutions. That one look all right? Any questions on it? It's kind of tricky, right? We can try that ABC, right? Is trig function equal to number, put theta equal to angle, then solve for theta in the unit circle, then figure out what x that is and restrict it. Now, the next case, case 2, well, suppose you want to solve a linear equation in a trig function. Maybe a little bit here. These are equations a times trig function, we said. Hope this isn't too much for b. Plus b equals 0, right? How do I solve that? We just return to algebra and we say, suppose we substitute u equals the trig function. Or actually, we don't even need to do that. Just subtract b and divide by a. Rewrite this as subtract b, divide by a, and get trig function equals minus b over a by algebra. Just like if you had ax plus b equals 0 in algebra, right? You subtract b and get ax equals minus b, then you divide by a, x is minus b over. Do the same thing here, but instead of x, you've got a trig function. So this is called a linear equation, one variable in algebra. This is a linear equation and one trig function. X is a trig function. Right. And then once you have that, its trig function equals a number, right? So you go to method 1. So that was the first build. We go to a linear equation. So here's another example. Suppose I had square root 3 times the secant of x plus 2 equals 0. This is a linear equation in secant, right? A times secant plus b equals 0. What do? I just try and write it as trig function equals a number. I subtract 2 and divide by square root 3. It's just algebra. You get trig function equals a number, right? Now I go to method 1. But secant, how do I get secant? So I left out of the instructions. You make them too complicated, they're just harder, right? You don't want to do it like you're writing a computer program for people. It's better they do some of it by themselves. When you have secant or cosecant, the trick is to rewrite it as the reciprocal. If secant equals this number, then the reciprocal of secant, cosine, is the reciprocal of this number, minus square root 3 over 2. Aha, that's a special number, comes from some sort of special angle. I can solve it on the unit circle. So if I want to solve that, I'll call this the x coordinate in the unit circle different from this x. I'd rather call this theta or something, but the homework uses x. So I'll say this is the x coordinate in the unit circle that I'm solving for. So I look at all points with x coordinate minus square root 3 over 2. And this x is not this x. I call this x hat or something if you like, x hat. And then that's close to -1 here. We observe that there's exactly 2 intersections on the unit circle, so exactly 2 terminal rays will have that cosine and hence this secant. And then you need to find all possible x. So this is A. You rewrite it as theta. Well, it's already just one variable, so it's already done. It's already just theta or theta equals x. There's nothing to do. And this is B. We're now going to solve on the unit circle like this. What is this angle here then? Since this goes from 0 to minus square root 3 over 2, we observe that must be a length of plus square root 3 over 2. This is 1 because it's a unit circle. It follows, this must be the 30-60-90 triangle, right? That's the only triangle that has these two side ratios. This one will be a half by the Pythagorean theorem. So that must be a 30-degree angle, pi over 6. By symmetry, this one is also pi over 6. All right, it'll be the same, square root 3 over 2 and 1. So this will be a half. Oh, symmetry always applies on these. And now I can figure the angles, right? If this is pi over 6, then this one must be pi less pi over 6. 6 pi over 6 less pi over 6 is 5 pi over 6. And similarly, this one is pi plus a pi over 6 angle, making 7 pi over 6. Now I have all possible x. Or what? 5 pi over 6 and 7 pi over 6. Now, if I do the same restriction here as I did on tangent, I guess we put it on there, that x has to be between 0 and 2 pi. Normally, I would have to now restrict it throughout all the angles that are bigger than 2 pi or less than 0. But since x is the angle by itself, all I found from this was all the possible x in 0 to 2 pi already. So I don't need to do anything more. I'll just leave it like that. This time, I don't have to add the 2k pi because I just wind up dropping it out when I apply this restriction. So there's all the solutions. Then remember these things build. So do you have any questions on that one? Because we're going to use that now to solve for the next method. Well, that looks fairly familiar. The next method is if you have a quadratic equation in a trig function. Three quadratic equations. Are these a times a trig function squared plus b times a trig function, same trig function, plus c equals 0. Why do we call that a quadratic equation in the trig function? Just for your mathematical ability in future classes, I would really like to generalize this a little bit. I think it really helps me to remember all these things when I see something like this. Remember what a linear equation in x is? So these are polynomials. Here's the degree of the polynomial. And more space. And here's its nickname, if you like, an alternate name. What if I put, and then the corresponding equation? What's a first degree polynomial mean? Do you remember that from algebra? In one variable x. Do this in more variables too. And again, this is just a note to generalize what we're doing. A first degree polynomial is a number times x to the first power plus a number, right? Just call it x plus b. First degree because the highest power of x is 1. That's also called, remember the name for a first degree polynomial? Called a linear polynomial or a linear function. So I'll say it's a linear polynomial. How about, I'll abbreviate polynomial poly. Now, what do you think is a second degree polynomial? This will be useful in your later classes, even though I won't test you on it. And I hope this will make this seem interesting. Second degree means it goes up to second power, ax squared plus bx plus c. We call this also a nickname quadratic polynomial. And now you remember something from algebra. What is a linear equation? I remember what a linear equation is. It's the easiest one.
Makes a line, right?
If you put y equals a linear polynomial, it does, yeah. That'll be a linear equation of two variables. I'm gonna do a linear equation of one variable. It's just a linear polynomial equals 0. But you're all right for two variables, yeah. So a linear equation in one variable is x plus b equals 0. A linear polynomial equals 0. A quadratic equation. So maybe I need a little more room here. So this is the equation. It's called a linear equation. Ax plus b equals 0 in x. If I put a quadratic polynomial equals 0, we call it a quadratic equation in x. Let's leave off the in x. So that's what a quadratic equation was. It was putting a quadratic polynomial equal to 0. And then you can go higher degree. We're not going to do that in this class, but I just wanted to show you can generalize this. And this is a really useful thing to know if you want to take calculus. These terms are thrown around all the time in higher mathematics, beginning with calculus mostly. But first degree polynomial or linear polynomial, second degree quadratic means a linear equation or quadratic equation. If you put a third degree polynomial, then you have ax cubed plus bx squared plus cx plus d equals 0. This is called a cubic, not equals 0, plus d. This function is called a cubic polynomial, or just a cubic. And you can go to fourth degree and say, oh, ax to the fourth plus bx cubed plus cx squared plus dx plus e is the fourth degree polynomial is called a quartic polynomial, or just a quartic function or a quartic. And if you put these equals 0, you call it a cubic equation, right? Ax cubed plus bx squared plus cx plus d equals 0 is a cubic equation. So all these terms follow rather naturally. This one equals 0, you have a quartic equation. And then, if I can put this over a little further, I guess, these all have nice solution methods, right? What is the solution to a linear equation we just said? It's the solution. I subtract b and divide by a, and I get x equals minus b over a, right? That's how you solve a linear equation. Subtract b and divide by a. How do I solve a quadratic equation? We need that today. There's a formula for it too. You do it by completing the square on this general equation. When you complete the square and solve it that method, you get x equals minus b plus or minus square root b squared minus 4ac all over 2a, the so-called quadratic formula. A formula for solving any quadratic equation. And then there's also a cubic formula. I'm not going to write it because it's too hard. I don't even remember it. There's multiple cubic formulas, actually. Some of them are easier than others, but they're all hard. And then there's a quartic formula. And you can take this higher and higher, and you can have quartic equations and trig functions and so forth, and solve those that way. Interesting result. I did this partly just to tell you the story. What if it's fifth degree or higher? Ax to the fifth plus bx to the fourth plus so on and so forth plus f. We call that a quintic polynomial. And when you write a quintic equation, ax to the fifth plus dot 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 plus f equals 0. Turns out there is no finite formula in algebra, no finite algebraic formula. So in algebra, you never go higher than fourth degree because it's hard to figure this out. You can sometimes guess a solution to this, but there's not a formula. So it's kind of an interesting result. We can solve these through fourth degree, and then there's no finite formula for higher. It's a pretty amazing result. Abel's impossibility theorem, they call it. There aren't solutions for fifth degree or higher. But the idea is you can take all the stuff we're going to do now with second degree and extend it, even if you get higher degree problems where you have third powers of trig functions or fourth powers. But fifth power, everybody runs into problems because you can't find a formula for it. So I'll just point that out as an interesting sidelight there and say, those are names you'll hear, and we'll refer to quadratic equations here and use the following method. Given a quadratic equation in a trig function, here's what you do. Let your favorite letter, U maybe, be the trig function. This one we can solve. Get a u squared plus bu plus c equals 0, which is called what kind of equation? Quadratic equation, right? So if you put u equal to trig function, this will come out to be a quadratic equation. We know how to solve that. It's the quadratic formula, right? That's why I'm putting it up there. This can be solved another way also. Sometimes the fastest way to solve it is by factoring. That often works, and when it does work, it's usually faster. Or B, we can solve it by the quadratic formula. That always works. It doesn't matter which one you use. You'll get a linear equation and a trig function. It might just be the trig function equal a number. And then go to method 1 or 2. Because that will apply after you do this. And the idea here is if you had a third degree polynomial in a trig function, you could solve it with a cubic formula with a lot of work. And then go to method 1 or 2 to find each of the solutions. And I'll just remind you so we can keep it up here that the quadratic formula for solving this is always u equals minus b plus or minus square root b squared minus 4ac all over 2a. Have to memorize that for the next test, which by the way is coming up a week from Tuesday. So probably on Monday, I will put out a practice test for exam 3, and it will be on chapter 7. It will go through solving trig equations, what we're doing today, and I might finish a little bit of it on Tuesday, but come this Tuesday, I'll finish all of the material. On Thursday, we can review, and then on a week from Tuesday, we can take a test on chapter 7, right? Probably the last material on Tuesday. But the idea is this: whenever you see one of these equations, go and write it as a quadratic equation from algebra, immediately use the quadratic formula or factoring. Once you have that, you have u equal a trig function, u equals these numbers, and you can go to method 1 or 2. There is one trick here, though. Remember what the quadratic formula has? How many solutions do you have here? Remember? Well, if b squared minus 4ac is negative, what happens? You get square root of a negative, and there is no real solutions, right? Square root of a negative number, there's no real number. If you want imaginary solutions, you can still do it, but we're not interested in that here. No real solutions. So you might get 0 solutions to this quadratic equation. And hence 0 solutions to your original equation. If this thing under the square root, we call this the discriminant, b squared minus 4ac. Does that sound familiar? If that's 0, then plus or minus give the same number. And you've got minus b over 2a, one real solution. But if this is a positive number, then its square root is positive, and minus b plus this is one solution, minus b minus this is the other, all over 2a. And you get 2 real solutions. So you can get 0, 1, or 2 real solutions out of this. And then for each of those, you can go to method 1 or 2. We'll illustrate that here, but let's see how it steps up and it steps up. The linear equation, you just, right, subtract b, divide by a, solve trig function equal to number. For this one, you can get 0, 1, or 2 solutions, and then you have to solve for each of them. Let me look at this one. This is kind of an interesting one here. We can do this both by factoring and by the quadratic formula, is the idea. This will be off the homework, this one here, so maybe look at it if you get stuck, what we did in class. It's 4a. Solve exactly, we want exact solutions, not decimals, on the interval 0 to 2 pi. The following 8 sine squared x plus 6 sine x plus 1 equals 0. How about that? Which method do I use? 1, 2, or 3? All right, each one built. Well, method 1 is for trig function equals a number. That's not of that form, right? Method 2 is a number times a trig function plus a number equals 0. It's not of that form. But I've got a number times trig function squared plus number times trig function plus number equals 0. This is a quadratic equation in the trig function. So I'm going to do what I just said here. This is by method 3 that we just wrote up here. Says 1, let u equal the trig function I see, sine x, to get 8u squared plus 6u plus 1 equals 0. Oh, a quadratic equation. From algebra, I know how to solve that, right? Let's solve this exactly by factoring the instructions. Say, I didn't write that down. You can do either method actually on this one. Let's do it by factoring. What does this notation mean? Remember this from algebra? What does that mean? It means whatever the variable is, x in this case, solve it for x between this number and this number. And the round bracket means don't include the endpoints. So you want strictly less than 2 pi. And the square bracket means do include it. So you want greater than or equal to 0. That's what that notation means. It's inequality notation versus interval notation here. All right. So now u equals sine x gives me a quadratic equation. And then by factoring, since we demanded to use that one of our 2 options here, how can I factor this? Remember how these quadratic polynomials factor? How do I factor this? And I usually say here that if you have some other method you're used to other than what I do, by all means use it. Don't let me confuse you by making you do it a different way that you're used to, right? People have a little different methods of factoring sometimes. If you can get it, great. Here's how I usually do factoring. Every, uh-oh, that was good, isn't it? Every quadratic polynomial that factors over real numbers factors as blank times u or x, whatever the variable is, plus blank, blank times u plus blank. So I'll factor the polynomial here like that because it always works when it factors. There's actually some of these that don't factor over real numbers. You actually factor them all using complex numbers, which we'll do a little at the end of the semester. But all right, think of this one, u squared plus 1. Suppose I have this equals 0. How do I factor this? I can't. Right? This actually factors as u plus the square root of minus 1 times u minus the square root of minus 1. We can't factor it with real numbers. Right? This has no solutions at all. And it's this case where b squared minus 4ac is negative. Anyway, so some of these won't factor because b squared minus 4ac is negative here. And you can try all day. You can't fill in the blanks with real numbers. But when it does fill in, it looks like this, and if you allow complex numbers, you can put numbers in the blanks here, it turns out, with i's in them, where it's -1. For this one, what I want to do, what do I know about the product of these two blanks? What goes in there? Product of those two blanks is always this number 8. Whatever multiplies u squared. And the reason is that when I go to FOIL this out, I'm going to take this times this, right? First, FOIL is first, outside, inside, last, right? Just all possible pairs. This times this will give first, and then this times this and is something times u, and this times this is something times u. This times this is a number. The only u squared terms come from this times this. So the product of this has to be 8u squared. It follows that what goes in the blanks has to be 8. Similarly over here, how about the product of these two? What's that product?
1.
Yeah, that has to be 1, right? Because, right? This times this gives u squared, this times this gives a u term, this times this gives a u term, but this times this gives only the number. So that has to be 1. That makes it easy to put in what to put in here. Either 1 goes here and 1 goes here, or -1 goes here and -1 goes here. Assuming you can put whole numbers in the blanks. Some of these whole numbers don't go in that case, factoring is just, you give up and use the quadratic formula. Here's the nice thing, quadratic formula always works. So if this factoring doesn't work, just use the quadratic formula. The idea of factoring is sometimes you can do it fast. But if you can't get it, just go to the quadratic formula. So I'm going to say if it was -1 and -1, that's not going to work too well. Assuming I put positive numbers in here, I'll get a negative here, u, and a negative here, u. I'll get a negative u's in the middle. So I'm going to put positive here to try and get a positive 6u in the middle. Put +1 and +1. Now that's the only way I can write 1 as a product of whole numbers. So now what goes in these blanks? Two numbers that multiply to 8. So I can try 8 and 1. Just try it, see if it works, right? This time this is 8u squared, check. This time this is 8u. This time this is another u, 9u. Uh-oh, that's not 6u. So that won't work. And then I get a +1, that would work. So this time this is 1. So let's try instead 4 and 2. But you just try the different possibilities. This time this is 8u squared, right? And two numbers whose product is 8. This times this is 4u plus this times this is 2u. The u terms add up to 6u, right? 4u and 2u is 6u. And then this times this is 1. Sure enough, that works. Let's write it a little cleaner here just to get rid of all the scribbles. I'll write the same thing though. 4u plus 1 times 2u plus 1 all equals 0. There it is. By factoring, I get that. And now what was the utility of factoring here for solving the equation? Or something called the zero product property. If I have two numbers, x times y equals 0, what do I know about those two numbers? Now you know this one. Either x is 0 or y is 0, right? And if the product's 0, then at least one of the two numbers is 0, maybe both of them. Same thing applies here. This is a number once you put in u, and this is a number. Either this number is 0 or this number is 0. That's the zero product property in order their product is 0. So equivalently by algebra, 4u plus 1 equals 0, or 2u plus 1 equals 0. So this original quadratic equation is equivalent to these two linear equations, right? Which we know how to solve, right? Just subtract b and divide by a. So that's the object here with factoring, is to take your quadratic equation, rewrite it as two linear equations, which is method 2, and now you can solve it. So this is equivalently by subtracting 1, dividing by 4, u equals -1/4, or u equals -1/2 from this one. And once again, why don't I write and? Why don't I write and these? I write or all the time. Doing a good job stumping you today, huh? The reason is that in mathematics, and means it has to satisfy both, all right? X equals 0 and x equals 1. I'm not saying mathematically that these are both solutions. I'm saying x has to satisfy both those. There's no solution, right? So and meaning it has to satisfy both. If I put or, that means it can be either one. So that's what I want here. You can be either one of these and satisfy the original equation. But that's it. Those are all the solutions, right? This equation has exactly two solutions. That's the case of the quadratic formula with b squared minus 4ac positive quadratic formula. Now we go to the next, now we go to method two. First rewrite it, I'm sorry, is in terms of the trig function, equivalently, this is sine x equals minus a fourth. Or if you put and, although you mean or, I'll just probably put a nasty red mark on there and not dock any points, right? Or sine x equals minus a half. And what I've done is rewritten this, maybe I should have called it method two back here, but I've got trig function equals a number, so I can go back to method one now. Sine x equals minus a fourth, I can solve on the unit circle because this trig function equals a number. Similarly, sine x equals a half, minus a half, I can solve on the unit circle. Number. And I just have to take the solutions from both of those, right? How do I solve sine x equals minus a half on the unit circle? This is what I don't like that the homework problems use x. I'd rather use theta, but this is the y coordinate of the unit circle, or we could call it y hat. Y hat equals minus a half is about like that. Here's all the points where the y coordinate of the unit circle is minus a half. We observe there's two such points on the unit circle, so there's exactly two terminal rays. Then we just have to find those angles, right? As before, we drop a perpendicular. We observe since it goes from x equals 0 to x equals, oops, I did this wrong, I did x. Y coordinate, I'm thinking x here. Y equals minus a half, sorry about that. Y equals minus a half. And there's 2 points in the unit circle here and here. And now I'll drop the perpendicular. Since it goes from y equals 0 to y equals minus a half, this side is a half. This is 1 because it's a unit circle. I recognize that triangle, 1/2 something and 1. This must be square root 3 over 2. And the angle here has to be pi over 6. Similarly, by symmetry, this is also pi over 6. They always come out the same. And I observe in the second case then, there are two solutions between 0 and 2 pi, right? There's this one, which is pi plus pi over 6 more is 7 pi over 6. Moving these a little faster now, right? And the one from here clear around to here, which is 2 pi back up pi over 6, right? I'm going to pull that one out a little slower. 2 pi less pi over 6 is what? Yeah, 11 pi over 6. As I rewrite this one as 12 pi over 6, common denominator. Subtract pi over 6 gives 11 pi over 6. There we go. So we've got two angles from this one. 7 pi over 6, which is pi plus pi over 6. 11 pi over 6. And since we're just dealing with sine of x, we don't have to go and take all solutions theta and then throw out the extras. We just already have all the ones between 0 and 2 pi. Now this one is starting to get hard. This one is harder. Sine x equals minus a fourth. Well, that's only about 1, 2, 3, 4, 1/4 of the way down. It's about here. Oops, throwing this the wrong way, am I not? And the sine x is the y coordinate. Y equals minus a fourth. Geez, that draw it backwards. wake me up here. Y equals minus a fourth is that one. Or hat, if you like. All right, and now there's exactly two terminal rays, this one and this one, right? That have that y coordinate on the unit circle. And unfortunately, when I drop the perpendiculars here and here, the side length is 1/4. That's not a special triangle, all right? I don't know what angle this is in here. Do I? What angle is this in here? So that's a right triangle. If I pull it out, pull this one out of here. It goes down 1/4 here. It's a unit circle, so it's 1 here. What is this angle theta that's in here? Should have called it x, but oh no, I want theta. I can use the sine, right? The sine is the opposite over the hypotenuse, so I know that the sine of theta is 1/4 exactly, right? Now, in a triangle, in a right triangle, if sine theta is 1/4, what do I know theta is for sure? It's the arc sine, right? So in a right triangle, there's only one solution to this equation, sine, trig function equal to number. Not all solutions, no matter whether it's right triangle or not. In a triangle, the only solution is the arc sine. So that's what this angle here is the arc sine of 1/4. Now, if that angle is the arc sine of 1/4, what is this angle? Exactly. Well, it's pi plus the arc sine of a fourth. There it is, that's this one. And I leave it in that form because arc sine of a fourth is not a special angle. And if you have bought one of those real expensive calculators I told you about, the Inspire with the computer algebra system, CAS written on it, and you put this kind of problem in here, we'll just leave it as arc sine of a fourth. That is the exact representation that everybody uses. So we'll leave it like that. Now there's one more angle within one rotation, right? We do all angles within one rotation. We go to this terminal ray and then we go to this terminal ray. We don't want to do this one minus arc sine of a fourth because we're going to restrict again to theta between 0 and 2 pi, right? So instead we want to go all the way around here, back up arc sine of pi over 6, right? By symmetry, this angle here is also the arc sine of pi over 6, of 1/4. I don't have to reinvent the wheel here, right? And so the final angle here within one rotation is 2 pi, one rotation, less that one. So there's the other answer, 2 pi subtract arc sine of a 4. And if you look on the back of your homework sheet, this is the answer to that problem then. Those 4 angles are the exact representations as best we can put them for the solutions to this original equation. Now, any questions? That was a pretty hard one, huh? That's about as hard as they get, though. Solve a quadratic equation in a trig function, all right? It's just AU squared plus BU plus C equals 0, where U is a trig function like sine. Put U equal to trig function to recognize a quadratic equation. Solve it by algebra. For each equation that you get from algebra, you can solve for trig function equals a number and solve each of them on the unit circle. So that's the recap of the whole method. So you really want to try these because the methods build like this. But that's as hard as we're going to do it. Let's try this one now. It's similar. I'm gonna save the last method for next time. The last method is, what if I have more than one trig function in an equation? So that'll be next time. Today we'll just do the one trig function in an equation. Let's try this one. Tangents, oh, actually I got two more here. I'm gonna do this one first. Yeah. Minus tangent squared x minus tangent x equals 2. And this time solved by the quadratic formula. Nice thing about quadratic formulas, it always works, where sometimes the factoring is hard to guess. Or there may not be any real factors. What do I do for this one? I first substitute u equal the trig function, right? Got from that minus u squared minus u equals 2. Now you might be tempted to say, where's the quadratic formula? Here's a equals -1, b equals -1, and c equals 1. Well, let's get rid of those minuses. Let's call it equivalently by multiplying through by -1. U squared plus u equals -2, multiplied all by -1. And I might be tempted to say, oh, u equals minus b plus or minus square root b squared minus 4ac all over 2a is, let's see, b is 1. A is 1 and c is -2 all over 2 times 1. And I've got it wrong there because I've made a mistake. In order to apply the quadratic formula, and this is the trouble with formulas, you have to put it in the exact form. You can't have c on the right hand, it has to be ax squared plus bx plus c equals 0. You need to get 0 on the right. So I'm going to do one more thing. I'm going to rewrite it as u squared plus u plus 2 equals 0. From which I observe c is at -2, it's c equals +2, right? So a is 1, b is 1, c is 2. It's a quadratic equation, and this doesn't apply. It's minus b is -1 plus or minus square root 1 squared minus 4 times 1 times +2 all over 2 times 1. Right? So that's what u is. And now I observe this is -1 plus or minus the square root of -7 over 2. What do I know now? No solution, I'm done. If this quadratic formula comes out with no solution, then the original equation had no solution. There's no number you can make u to make this work, and there's no number, no tangent x that'll make it work either. So no solution. If you want, you can put this for the empty set. Right? But when the quadratic, see, it's a good thing we didn't try and factor. We would never have been able to factor it using real numbers. It doesn't factor with real numbers. On that one. So some of them you'll get this, and you have to put them all, put 0 on the one side and apply the quadratic formula. Sometimes there'll be no solution. In some sense, that's easier, right? You don't have to do all that unit circle work. And now finally, this next one. Ran to OOPA here. Suppose we try this one. This is 5a. If I take tangent squared x plus 5 tangent x equals 1, solve, again, on 0 to 2 pi, that is x in radians between 0 and 2 pi, not including 2 pi. What I first want to do, now I'll put it equal to 0. We'll put tangent squared x plus 5 tangent x minus 1 equals 0, so it's in standard form. And then I'm going to put, you don't actually have to put this in, I like to put it in. Observe the quadratic equation, put u equals tangent x, I get u squared plus 5u minus 1 equals 0. Once I have a quadratic equation, I can solve it by the quadratic formula or by factoring. This time I'm going to be glad I used the quadratic formula though. If you try to factor this, you'd be all day guessing the factors. It actually does factor, unlike that last one. But here's what you'd have to do. U equals minus b is minus 5 plus or minus square root b squared 4 times a times c all over 2a. What have I got? Minus 5 plus or minus the square root of 29 all over 2. What if I tried to factor that? What would I get? You know how this would have factored? See this from algebra? How would this have factored if I used factoring instead with 1 here? This would have factored as the lead coefficient 1 times u minus the first of these solutions times u minus the second. And then all equals 0. So had I tried to factor it, I would have had to guess to put these in the blanks. Minus 5 plus square root 29 over 2. Minus 5 minus square root 29 over 2. Factoring, sometimes this doesn't work because you can't guess the factors, even though there are factors. Right? So good thing we didn't try and factor. We used the quadratic formula. But that's what would have happened, just for your algebra interest there. Now, these are the two solutions. So we go to method 1, right? Because after all, u is equal to tangent x. Right? So put u equal to trig function, solved by the quadratic formula. Now you can go to method 1 because it's trig function equal to number. There's actually 2 of these equations, right? One for the plus sign and one for the minus, because I get tangent x equals one number, tangent x equals a number. Another, so what I'm solving here is, let's put it, I better put it on the next board. It's 2 different trig function equal a number equations. Tangent x equals the first number, minus 5 plus square root 29 over 2. And tangent x equals the second number, minus 5 minus the square root of 29 over 2. Those certainly don't come from special angles, so I'm going to have to use inverse trig again. But I still solve it on the unit circle. Right? Now, how about if I solve this one by method 1? Trig function equal a number. I'm going to go put it on the unit circle. I don't have to plot this real accurately, but I do have to plot it in the right quadrant. Square root 29 is bigger than 5, right? Square root 25 is 5. This is bigger than 5. So this whole number here going to be positive or negative? Be positive, right? Minus 5 plus something bigger than 5 will be positive over positive 2 is still positive. So this makes tangent x positive, which means the angle is in quadrant 1 or quadrant 4, maybe something like that. It doesn't matter, just put it in the right quadrant. Quadrant 1 works and quadrant 4 works. Remember, whenever tangent x equals a number, there's 2 solutions within one rotation. One of them, and they're always opposite quadrants, directly opposite each other. And what is this angle here? I know what this one is. How do I know what that one is? How tricky this gets. You have to practice these. Do practice these because, like I said, a week from Tuesday, you got to be good at it. I'll give you one like this somewhere on there. One solution to this, tangent x equals the number, is always the inverse tangent, right? Which one of these angles is it? Is it this one, or is it this one, or is it this one? This one is the arc tangent. X equals arc tangent minus 5 plus square root 29 all over 2. And I know it's this one, not this one, because arc tangent is the solution that's in the first or fourth quadrant between minus pi over 2 and plus pi over 2, right in here. So it has to be this one. Now, if that's the arc tangent, what is this angle? So what is this angle here, the other possibility? By symmetry, this is also the arc tangent of minus 5 plus root 29 over 2. So this angle is pi plus that arc tangent. What we observe is that there's these solutions within 0 to 2 pi, arc tangent 5 plus square root 29 over 2 and pi plus the arc tangent minus 5, I'm sorry, minus 5 plus square root 29 over 2. That's the two solutions corresponding to the plus sign here. But wait, it's even more complicated than that. We also have this one. Let's write it over here. For the second one. I can also solve on the unit circle, right? Tangent equals this number, I solve on the unit circle, tangent x equals this one. This one is negative, right? Because I've got a negative minus another number, right? Two negatives here, it's still negative. If this is negative, then the angle is in quadrant 2 or 4, right? Tangent is negative in these two quadrants. I don't know exactly where it points, it doesn't matter, just put it in the right quadrant. And one of those is going to be x equals, one of those is going to be the arc tangent of minus 5 minus root 29 all over 2. Which one is the arc tangent? That'll always be one solution of this. Arc tangent is quadrant 1 or 4. In quadrant 1 it's positive, in quadrant 4 it's negative. Here we have the negative one. But it's not this one, it has to be in one of these two quadrants, so it's this angle right here. Right? So what angles do we want for this? What are the solutions? There's a solution here. What angle is that? Pi back up this angle, which is pi actually plus the arc tangent of minus 5 minus square root 29 over 2. Why didn't I subtract it? Because this angle is already negative. If I take pi and add a negative angle, it'll take me back to here. So that's what this angle is. And then this angle here is the other one. I don't want to go this way. I don't want to take arc tangent because it'll be a negative angle. I want an answer between 0 and 2 pi. So I take 2 pi plus this angle. There's my answers, right? So I'll take this arc tangent plus pi, this arc tangent plus pi, and this arc tangent plus 2 pi. Are the 4 exact angles. Now you're experts on solving trig equations. Right? We said to do all those others in the other sections. This one is 7.5, I think. I think you do 1 through 6 now. Try those and make some questions the next time. Yeah, that's right. Actually, we drop out number 1. Let's just make it 2 through 6. Sort of a general concept question. Hey, thanks for putting up with me today. Again, next time. Here.